A few words on the model we have used in this work. This is a cohesive zone model, which is based on the pioneering works of Leonov, Panasyuk, Dagdale, and others in the 60s of the last century. The idea is clear. The prefracture zone along the crack line is modeled by the slit with constant or changing stresses on its edges. This work was used by us and other scientists from Ukraine to analyze the problem for the interface crack. The following three works can be used to line up the material on this topic. This model is part of a modern cohesive zone model, which is firstly introduced by Needleman and further developed in the work of the following paragraph. We use the simple Brittle criterion of the mesoscale type to generalize this model for the adhesive joints between two dissimilar materials. Next slide, please. The problem statement is simple. We have some small-scale prefracture process zone along the crack line. The crack length is L big, and the process zone length is L small. We apply the following boundary condition, which is described with notation of the other formulas in this work on the slide 3. Not deepening into the details of the analytical process of the solution, we simply cut the process zone and the material on along the crack tip, and use the Wiener-Hopf technique with factorization by Hrabkov to derive the governing equations, which can be used to determine the process zone parameters. It is not that hard with modern computer algebras. You can see it in the slides 4. Next slide, please. Five. Next slide. And 6. The asymptotics are shown in equations 10, 11, and 12 on the slide 6. So, after applying all these methods, we can use the complex function to obtain the solution through the formulas on the slide 7. These governing equations are the equations 13 and 14 on the slide 8. We have used convenient notation, which can be applied to these formulas to analyze the structure of solution and give some useful conclusions. Next slide, please. To apply displacement criterion to this problem, we should calculate the jumps for the displacement on the crack line, which is given by formulas 15 and 16 on the slide 9. It is simple quadratic equation for the opening displacement criterion. Delta n and delta tau are the critical values of the opening displacement. It is widely used to formulate criteria for the finite elements method in the terms of energy. And this is done by the formulas on the slide 10. We used three values for the powers in the criterion 18, namely 1/2, 1, and 2. Now, some numerical analysis. We have two dissimilar materials with the same Poisson ratio, and ratio between Young moduli is equal to 0.25. On this slide, slide 11, we have a series of curves which corresponds to various values of the powers in equation 18. These curves can be used to analyze dependence of the parameters of process zone on the stresses at infinity. Next slide, please. This slide is for the phase angle, opening displacement, and relative value of the process zone to the general crack length. Next slide. For various phase angles of the loading at infinity, we construct some curves that can be used to analyze how the process zone parameters depends on the phase angle or ratio between sigma 0 and tau 0. Energy depends on the ratio between Young moduli of the materials, and we construct some plots on this on the slide 14. For the sake of brevity, we only use values lower than 1. Now some experimental background. We compare our data with experimental data from the work Katsivalis, Thompson, and others on the slide 15. Mild steel, tempered glass, and two adhesives. One of these adhesives is relatively brittle. The other is a plastic one. We found that our theoretical results is well aligned with test results from the experiment for the one adhesive Aduit 2020, but diverges for the other as it was plastic one. So this methodology cannot be applied to the plastic adhesives. Some conclusion on this work is explained on the slide 17. Many thanks for your attention.